Hello, and welcome to Groups Without Algebra. This will be a video showing some properties of groups and symmetry without using any algebra. I'm Josh, and I'll be leading the video today. So today I want to talk about wallpaper groups. So what is a wallpaper group? Well, if you think about a tiling in a bathroom or in a kitchen, or if you've seen tiles on a wall in a public place, you'll see that they kind of follow a pattern, right? They follow a pattern, and however big you make that wall or however big your backsplash is, that pattern can continue forever. And it's typically a symmetric pattern. So it looks kind of the same however long or wide or tall the tiling goes. So this is kind of the idea behind wallpaper groups. Wallpaper groups are a way to cover the plane. So if you think of a two-dimensional space, like an infinitely big wall or infinitely big table, that's the plane. And so being able to tile the plane using some kind of symmetric pattern or a pattern with some kind of regularity and symmetry, you can think of in terms of groups. So to do that, let's talk about this tile. So this is a tile that I've made, and I made some of these kind of as a nice aid for explaining this concept. And the first thing I want to define is an isometry. So what is an isometry? So isometry is an operation that preserves distances. So that's a fancy math way of saying that it doesn't change like the rigid structure or something. So you can think of this tile. So an isometry could be, a way to move around this tile without shrinking or changing it in any way, like shrinking or growing it. So what are some isometries that we can do? Well, we can define some in a way that makes sense. So the first kind of isometry is something known as a translation. So translation is something that kind of shifts or moves around the shape, or it preserves distances, but without any kind of spinning or without any flipping. So for example, if I take this and I slide it up diagonally here, that's an example of an isometry. So to kind of represent this translational isometry with this rectangular tile, I have an identical tile, and I put some lines on it to kind of represent the isometry. So if you think of this tile, we're going to shift it up this way. That is an example of a translation. And if you take this pattern and you repeat it, you could repeat it infinitely and kind of tile up this way. And then if you start with the tile down here and tile that way, you could tile the plane. So this is an example of a subway tiling. It's a very common tiling. If you Google subway tiling, you'll find lots of DIY videos and videos of people tiling bathrooms or kitchens with a subway tile. So translation is when you shift around a tile and you don't introduce any spinning or rotation. So that's one kind of isometry. So another kind of isometry is rotation. So rotation is when you spin something. So you kind of choose a point and you rotate around that point. So I could do something like I could take this corner, pretend it's fixed in place, and then I could rotate it up that way. And I could rotate it 90 degrees, as I've just done. I could rotate it something like 45 degrees. I could rotate around another point. I could rotate like around the center kind of thing, like this. It's known as a rotation. So to kind of represent this rotation operation, if you will, I have this tile and I'm going to kind of, loosely stack it on the first, and I'm going to rotate around the top left corner like this. So that's an example of a rotation. So this is another kind of isometry where you kind of fix a point and then rotate around that point, and you get another pattern. Coincidentally, this has a very common name in kind of tiling and design. This is known as a herringbone pattern. So I can also put this here if I wanted to rotate around another point. Again, if you look up DIY videos, if you look up videos on tiling various things, floors and bathrooms is a popular choice for this one. You might look up herringbone and find patterns that look like this with rectangular tiles. So this is another form of isometry. This is another thing. So what else can we do? Well, what's another way we can preserve lengths and kind of shift this tile around without shrinking or growing it? Well, you can flip it over. You can flip it over like this, right? And this you can kind of think of as a reflection. You're reflecting. You're taking 2 points and making a mirror reflection of them, to the right or to the left or up or down, right? So this is another form of isometry, and I can represent that with a handy dandy tile like this. So as you can see here, you can kind of imagine if, we have 4 points on the original tile, this point gets mapped here, this point gets mapped there, this point gets mapped here, and this point gets mapped here. Okay, so you have kind of reflection, and you can see it's reflected in the line, right? You can see that the line is reflected. It's like a mirror image of itself. So this is another form of tiling. This is another isometry that you can think of. Reflection. And I mean, you could reflect it this way, you could reflect it up here like this. There's different ways to think of reflection, okay? And again, this line is just for, I made these tiles as sort of a visual guide, right? So that you understand that this isn't just the same as a translation, it's actually a rotation, okay? So there's one last operation that you could do. There's one last isometry, and it's called, in the math literature, a glide reflection. So a glide reflection is kind of like flipping around a point. So here, when it comes to reflection, we kind of flipped around 2 points. Let's say we flip around just a single point. Like for example, I might flip up this way, or maybe I'll flip, if I choose this as my fixed point, I could flip up like there or something like this, right? So again, like the tile goes upside down, but I'm still preserving all of the lengths on my tile. So by this. So again, like if I were to like somehow flip it up here, I would get something that looks like this. Get something that looks like this. And again, the lines are a helpful guide that I've actually flipped over the tile, but for kind of aesthetics and also learning purposes, I've kind of kept it in here. So this is a glide reflection. Another way to think of glide reflection, which is really helpful for me, is to think of like footprints where like they're kind of reflected on each other, but they're also gliding and sort of moving forward. So in general, those are the 4 kinds of isometries that you can think of. I've used rectangles. You could also use other shapes, hexagons, triangles, etc. But these will tile the plane. If you continue these patterns infinitely in different directions, you would be able to cover the entire plane without any gaps. Again, if you think back to your subway tiles in your kitchen or in your bathroom, herringbone pattern in a bathroom floor, like they would cover the entire floor. There'd be no gaps. So these 4 kinds of isometries are elements in a group, or can be kind of put together in a few different groups called the wallpaper groups. And the wallpaper groups are exactly what it sounds like. If you want to cover a wall infinitely large or infinitely not so large, you can use a combination of these 4 isometries to get a repeating pattern, right? Which is a form of symmetry. Groups are all about symmetry, and these kind of show another angle of symmetry of like how could you infinitely and symmetrically cover the plane. And so that's it. Thank you very much for listening and for watching. This has been Groups Without Algebra.